Okay, this is the beginning of video 16.6, weak acids. It'll be a series of videos, and then we'll talk about weak bases tomorrow. And that will lead us right into titrations, and then we'll have our test. So this kind of brings us back to where we were. Remember that this, if I look at which diagram represents a weak acid, if this is HA, right, then here notice that these are all associated. I've got a couple in here that are not, but this is 100% dissociated, right? And so this is strong. This is also a single arrow. And when I solve, what we saw in the last video is that when I have a certain molarity of acid, it's going to go all the way to completion, and I can directly calculate, using stoichiometry, the molarity of the acid I have, and therefore the pH. So that's an easy stoich calculation. This is going to be a little bit different, but we did it in the last unit. Remember, now I don't just have A goes to B, I have all my species existing together in the same reaction vessel. So I have equilibrium concentrations of each that I have to determine, and so that's going to mean Rice tables. All right, so this one is on the left. Now, when I'm going to write these, there are two ways. Remember this. We can take HA, if it's a weak acid, and we can write it as H plus A minus, or HA plus H2O goes to H3O plus A minus. Now, if you look at your equation charts, let's look at those now, right? So everything that we're going to be doing in this unit, see, there's KC, there's KP, everything is going to be from here down. And notice that they did not include water in the expression, so hydronium ion is not in the expression. Now, when you do bases, you'll see that water will be in the balanced chemical equation. We'll tackle that when we get there. But here's the expression we have. So for the most part, we're going to be using, for acids, right, this expression, right? And remember, this is a weak acid. This is a strong. All right. Now, just like with any equilibrium, we have an equilibrium constant for acids and bases. For acids, it's called Ka. So if my reaction is HA in equilibrium with H plus A minus, then Ka is going to be the concentration of my products divided by the concentration of my reactants. Or if I wrote it the other way, I could also say concentration of H3O plus times A minus divided by the concentration of HA. But most of the time I don't need to do this because I don't have it's not an aqueous, it's just a liquid acid. Okay. All right. Now, another thing that we know, remember we talked about KSP. And KSP, the higher KSP was, the more dissolved the salt. This is going to be true of Ka. If Ka is high, that means I have a lot of that. So when Ka is greater than 1, I am product favored. And high dissociation. Therefore, if I'm comparing two, now notice these are not product favored, so if Ka is less than 1, I'm reactant favored. And low dissociation. So what that tells you, this makes sense, doesn't it? These are both less than 1. That means they don't dissociate. And we have primarily this species in our beaker, just like what we saw in our picture. But I can compare the strengths of acids by looking at Kas. The higher the Ka, the more H plus I have. So in this case, this is going to be my stronger acid. Just because the stronger acid needs to have lots of that means a higher number. Now, remember we looked at some weak acids. We wanted to I said I would kind of go back to the carboxylic acid. These are not written always in the same way you might see a regular acid where the formula starts with an H. It may look like this, where the H is on the end. These are carboxylic acids. These protons here are very acidic because there's a whole resonance thing going on here. Remember that from I can't remember which unit it was, like unit 9, I think, or no, I can't remember. Anyway, that you've got this resonance thing going on here, so that stabilizes this, and that can pop off really easily. Okay, but that's a certain class of acids, and so we're going to work our first problem with this kind of acid. So the first kind of problem that we're going to work is if you are given the concentration of a weak acid and the pH of the acid, it is possible to calculate the Ka. What we're going to do is we're going to walk through the steps really slowly, and I think you'll recognize all of this. This will make perfect sense. So the first thing we're going to do is we're going to show the dissociation of nicotinic acid, and we're going to write it like this. And that gives H plus C6H4NO2 minus. Notice that we're not going to put water in this equation. Let's write my Ka, my acid dissociation constant, which is just going to be products. C6H4NO2 minus over HC6H4NO2. Now, it says here a 0.02 molar solution of nicotinic acid has a pH of this. So it's telling you what the pH is. If I know the pH, I know the concentration of H plus in this solution. Now for a strong, so let's look at it, right? So I can still take this value and use that to determine the concentration of H plus. So let's do that. The concentration of H plus is going to be 10 to the minus 3.26, which is 5.5 times 10 to the minus 4 molar. Now, here's what I want to bring to your attention. If I had just used, if this were a strong, and I had 0.02 molar of this acid, I should have 0.02 molar of hydrogen ion. The pH of that solution would be around 1, or the hydrogen ion concentration of that solution would be 1 molar. So you can see already that this acid is not completely dissociating. It does not go, all of this does not go to hydrogen ion, and so my pH and my hydrogen ion concentration actually is lower and my pH is higher. Okay, so that's going to be useful. So let's look at that. Now, what we want to do is we're going to use that number and we're going to calculate Ka. Okay, so let's put our set our rice table up. C6H4NO2 H plus C6H4NO2 minus. All right, so where did we start? Well, the problem on the other page, this page says, I have this much nicotinic acid. So I have this much of my acid, and I don't have any of those. My change. Now, what is my change going to be? Well, what we can do is we know this concentration, right? So let's put, this is X minus X. This is plus X. This is plus X. So my equilibrium concentrations are what? 0.020 minus x, x, and x. But I know this and this, don't I? I know these because we calculated over here that our concentration was 5.5 times 10 to the minus 4. So I'm going to substitute that in. That is my hydrogen ion concentration, 5.5 times 10 to the minus 4. This is 5.5 times 10 to the minus 4. And this is 0.02 minus 5.5 times 10 to the minus 4. And that turns out to be 0.19 molar. Okay, so the pH gave me all of these values. So all I have to do is plug them in. Ka is going to be this times this divided by that squared times 10 to the minus 4 molar squared times 0.019 molar, and that is 1.6 times 10 to the minus 5. So all of this you have done before. You have seen this before. This all makes sense. The only difference was, instead of giving you X in the terms of a molar solubility or finding it through total pressure or telling you what the concentration is, we gave you a pH, and that's how we got here. Now, in order to determine this, how much of our acid actually dissociated, we're going to calculate what's called a percent ionization. Now, this is going to come to be a very important number. Percent ionization is equal to the concentration ionized divided by the original concentration. So it's part over the whole. How much of the whole molarity was actually ionized? So what that's going to be is my X. I'm going to take 5.5 times 10 to the minus 4 divided by 0.020 molar times 100, and that's 2.8%. Because X tells me how much of this solution became ionized, which is the change. X is the change, and that tells me it's sort of like molar solubility, but for acids. So I'm going to take that concentration ionized, divide it by the total, part over the whole, times 100. This tells me that this acid is 2.8% ionized, and we'll see in a couple minutes about why that's going to be very important.